Okay, so now we're going to start working through actually some of the whole sort of folder full of files and script files that are available to go along with this sort of series of podcasts. And especially we're going to do this because now we've just in the previous podcast we've covered the difference between our scripts, our Markdown, and our notebooks. So the files, as I said, we've made are all in our Markdown format, and you can find them here they're hosted on GitHub. So GitHub I'm not going to go into in this podcast very much at all, but just to say GitHub is like an online repository for developers to develop code, share projects, and host a lot of files. So you'll see here, this is my page. We've got a load of different files and projects that I'm working on and contributing to. But the ones we're looking at are actually being developed and held by my colleague and collaborator Alan Zidic. So these are down here. So I have a link for this somewhere for you, but if you go here on my page you'll find it eventually, or if you go to Alan's, it's here. So we click on that and that will take us to this project called R Lectures that we've been working on. So in here you can see we've got a whole bunch of folders that we're working on and developing and adding content to. So the best thing, if you want all these files, you'll get not just the HTML files that you can link to off websites and you find them that way, but you can actually get the raw Markdown and build these all yourself and edit them if you want as well. So if you do want to get this whole suite, and that's what I'm going to kind of work through this over the next little while, you go here to clone or download. So if you're familiar with GitHub, you'll know what you're doing. If you're not familiar, the thing to do is go here to clone or download, hit download zip. That will then start a download. It shouldn't take too long. It's not a huge package. So just fast forward through that. It took a little while on mine. Connection was a little bit slow, probably GitHub's fault. But we now got our zip file downloaded somewhere. So we just, wherever it is on your computer, you need to go find that. Find that here. And then you'll just double click on that and it'll unpack it somewhere. So this will unpack it here into my downloads folder itself. But now you've got this R Lectures master, and that's because there's a master branch. There's different branches you can work on GitHub. So inside that you'll find all those files. Now you have to access to those as well. So there's today's lecture. There's lecture 2 essentially. It's got a series of JPEGs and data that were used to make the Markdown file that we'll see in a moment, but also then it has the raw Markdown file there that you'll be able to work with. So if you want that, that's the thing to download and get. And you'll see one of the things you'll get is you'll get an R Lectures project file, R proj file. So if you double click on that, that will open up for you. Although before you do that, I'd suggest you move this whole folder. I would take this whole unpacked folder like this and I would move that somewhere sensible. At the minute it's in my downloads folder. It's a silly place to be working. I put that away somewhere safe on my computer. Once it's somewhere safe and sensible, you then double click on that and that will open up RStudio and you'll get something very much like what I'm going to show you now in a moment. So I've already done this, of course, because I'm actually working on these files and I have them in my projects file already. So we'll switch to RStudio. So this is what you get. You double click on that R project file. Remember, we've covered that already, so you know what these are. That's then loaded up the project file. It's taken me to this directory. It's showing me the files in that folder, and then up here it's showing me that we're working on the R Lectures project, and again up here it's showing me that we're working in the documents, my home directory, my documents folder, my projects folder, and I'm working in this other folder called R Lectures, and then it is a master branch. It's clever. It's spotted that it's a GitHub repository, so it's working on the master branch, and then it's just an RStudio project that we're working on. That's what you'd be facing with. So today's one then, we're going to click on into and open it up. We've already done lecture 1. I haven't shown you that already, but you can find that in there from the other day. Lecture 2 is here. So we'll click on that, and what we're going to do is work through this Markdown file, this l2.rmd Markdown file. So if we open that on up, I'm going to minimize the environment here because I don't really want to see that. And I'm just going to knit this straight away so that we can see it as well. So that's what the raw Markdown looks like. With a bit of time and practice, you get to just be able to read this, I find, and you don't even need to have the HTML beside you. But at the beginning, you might like to have this or print out the HTML and have it on your desk while you're working. So we'll knit that. We'll knit that, and then we get this. We have our document that we can work on. Yeah, so we can just start working our way through this. So we're going to start, we'll show you how to clear the console window, I'll show you that in a moment. How to create a folder on your local computer, we've already done. So you've actually already done that in the previous podcast, and you should have, and if you've downloaded this whole directory, you would have just done that as well with the project file. And I'll talk about this now in just a moment. So let's go back here, open up my console window. So as you can see, sometimes you might want to clear a console window. So at the moment, there's a couple of things going on actually here. I have a load of code already typed in, because I was working on this project already just before making this podcast. And you can see here, if I click this, you'll see in my environment, I've got things already in my objects already in my environment that we're going to work on in a moment. So if this is the case and you want a clean start and you want to start again fresh, the thing in RStudio to do is to go up here to the session window and check restart R. So this will start a whole fresh version of R. So it's saying it's restarting the R session. It's cleared out the environment, so there's nothing hanging over from any previous work that we've been doing. And that's a really good trick. So at the end, particularly at the end, when you think that you're finished your script and you think whatever analysis you're doing, when you think you've finished it, really good trick, something you should do out of good practice, is restart the R session and try to run your script again from beginning to end, the whole thing from beginning to end. And if it doesn't run clean from beginning to end, then there's a mistake in there. And the reason you haven't seen that mistake previously is because obviously you probably did something and specified something manually, or there was some object hanging over from a previous work that you were doing, but it's gone now from the script. And if your script doesn't run from start to finish with all the information and only the information it needs, then you've made a mistake. You need to try and go back and make sure that it works. We've restarted R, but really the trick is to clear the console. The other thing we might do is just want to see all this. We can scroll back up here and see all this previous work that I've been typing on here. We might just want to get rid of that. So one way to get rid of that is just a very simple shortcut, is to hit Control L. I think it's the same on Mac and on Windows. So hit Control L, and that just clears the console window for me. So there's nothing there for us to see. It's just nice, clean looking start, and we can get working. So just a little note then on why we work on these directories. You'll see that we loaded up the R project file, and it's taken us here to this directory here. Inside that there's a whole bunch of folders. Now when you come to do your analyses, what I've said is that actually inside each one of these subfolders, if this was like an analysis for your project or an analysis for a paper that you're working on, inside each one of these you would probably have they would have their own R project file that would be specific to those projects. But this whole thing for me, as I'm developing it, is itself a project. So when I load it up, I get taken to here. Now the point is that actually right now we're working in this folder L2. So we're going in here to L2, and this is where all my files are, and this is where we're going to be working. Now just to sort of make the point of this, if you work on an R project file like I suggest, and you work in a folder specifically, and inside that folder are all your documents and your files, then you don't need to worry about this setting a directory. So setting directory basically means that R, like many computer programs, it can't see your entire computer. It doesn't know where all your files are, and that's a good thing. That's because you might have the same file name in multiple different locations. So it's actually good that it's very specific about this. So within a folder, so when you load it up, it loads to a working directory, and that directory is the only one that it can see. So we can see here, if you want to see what the current working directory is this getWD, get working directory function. So if we run that, it says I'm currently working in, over here on the console now, I'm currently working in users, Andrew Jackson, documents, projects, R lectures. So that's where I'm working. So I'm not working in L2, I'm actually working up here in the R lectures. This is where my working directory currently is. And this is where it will look for files. This is where it will write to. So if I make a figure and I save it with R to somewhere, this is where it will save it to, into this folder here, not into L2. So if you wanted to change that manually, you can. And there's three different ways you can do that. You can either use this set WD function, so we're not actually going to run this code here now, but you can have set WD, that's set, so get working directory gets the working directory, and set working directory will set it somewhere. And this is how you'd set something in Windows typically, usually to the C drive, /users, username, whatever. Or on a Mac, you would set working directory to /users, username, or the root symbol or something. So just like mine up here, this is users, my username, my documents, wherever it is that I'm working. So you can actually hard set a working directory wherever you want on your computer with that command. So You can use get working directory to get it, and use set working directory to set where you are. The other way to do it is you can do it sort of manually up here on the window through RStudio. So you go up, you can go up. Where is it here? It's in R. It's on in Mac. It's on session. So it's session, set working directory. Then you can choose directory. You can set it to wherever the files pane is currently pointed. You can set it to wherever the source file you're working on is. You can set it back to the project directory, the original project directory, or you can choose any directory on your computer that you want there. The same options exist if you're working on Windows. They're just somewhere slightly else. They're just under the Tools option instead. And the third way to do it that sort of makes sense is here on this on this window here. You can go to the Files pane, and just because the Files pane is somewhere doesn't mean that the working directory is there. So if I click in here to L2, I've changed where I'm viewing my files, but my working directory, my getwd, is exactly the same. It's not the L2 folder. It's one up above from that. So we can check. We could, if we want, change it to here, and we do that by finding the folder in which we want to be here in the Files pane. Go to More. Check set as working directory. Now what we do is if we do getwd here in console, it'll see that it's changed, and now our working directory is moved from R lectures to R lectures/L2. So this is now where we're working. I'm just going to change that back. I'm going to change that back using session set working directory to project directory. And it's set it to there. It's changed the view pane here in the files, and I'll just double check. Go to getwd. Sure enough, we're back in the project directory again where we want to be. So that's three ways of changing it, but I'm showing you that more to show you that it is possible, and just to bear in mind that if you're typing, if you've got a script that points to a file and R is telling you that file doesn't exist and you're sure you've spelt it correctly, chances are that your working directory is not correct, and you either want to change the working directory or set your project up differently. But really, if you work with these project files like this whole working directory thing, generally speaking, shouldn't be a problem unless you start putting files elsewhere on your computer and you want to pull them into a different project, which definitely can happen in more complex, larger projects. So we've already knitted out. So let's move on. We've already knitted the file. We've already seen in a previous podcast that how the Markdown text and code works. So I'm just going to change some spelling mistakes here as I see them. We've learned out how to do that. We've done our shopping list. We know how to execute code and send it over from here. We're just going to move on kind of quickly now. So we're going to start looking at a script like this. So now our script file really is only beginning proper now. So this, we're going to start looking at entering some data. So if we, again here, we're just removing the list. So we're going to remove anything in the environment. Actually, if we look down here, there's nothing in the environment anyway. So running that sort of does nothing right now. And what I've done is I've gone on, I've just for sake of getting some quick data, I've gone and measured the finger lengths and my digits on my left and my right hand, and I've jotted them down here. So we've got my left hand finger lengths from thumb, first index finger, second middle finger, third ring finger, and then fifth is my little finger. So that's the left, so we know how to do that there. So my left fingers, there they are, we'll see them in the console, and they've appeared here in the environment. The right finger, similarly, and if we can again just check the class of them, the left fingers are numeric, the right fingers are also numeric. And then if we want, we can bind them together. So those are two single vectors, but there's a function called cbind, which is like concatenate bind, and actually it's column bind. It'll bind them into columns. So let's just run that and see what it gets. So if we cbind left and right, over here in the console, we see what we've done is created like a matrix. So we've got two columns of data here. We've got left and right hands for 1, 2, 3, 4, 5 fingers. So one thing that's interesting is I've just stored that there. So that cbind left right thing, it exists because we can see it over here in the console window, but it hasn't appeared in the global environment, and that's because we haven't assigned these to any object. So whilst R has evaluated that and returned an object, it's returned it sort of silently and hidden, and it's actually trashed that object already. So nothing actually points to this object that we can see here. So it hasn't appeared in the global environment. If we wanted it to appear here, we'd have to give it a name, like my data or something if we want, but we won't worry about that now. You don't need to do it. So we might want to plot some data. So the first thing I would do always after getting some data in is probably look at some summary statistics of it and do some quick plots. Now the way to plot data is always as a scatter plot. Your data is always a scatter plot. There's no other type of plot in the world basically. So where each data point exists as a point or a dot or a star or some sort of thing, usually in two-dimensional space, maybe 3 dimensions, but normally for us it's going to be in two-dimensional space. So we want to plot our data. So there's lots of different ways of doing that, and we're going to have a quick look at that here now. We're not going to look at plotting, making these plots really neat and tidy just yet. We're going to spend more time doing that in subsequent podcasts, but now we're just going to get a quick feel for what the data look like and to show how a script might look from beginning to end. So I've got a chunk here called scatter fingers. It's going to produce a scatter plot. So these data are not that amenable to plotting as I want them just yet. So we need to just change them a little bit for this particular example. So I have to put them all into one big long line. So we need to put the 2 finger data together, so not side by side like this over here with the cbind, but all just in one vector with the concatenate C function. So I'm going to create an object called fingers. That's the left and the right data together. So we can see what that is over here, fingers. So there's the first 5 entries there are going to be the left hand, and the next 5 entries are going to be the right hand, so it's left then right. Now we need to be able to identify that this is the left and this is the right. So this data point here is from the left hand, and whereas this data point here is from the right hand. So to do that, I'm going to create another object here. I'm going to call that one hand, and again what I'm going to do is I'm going to encode the left hand as the value 1, and I'm going to encode the right hand as the value 2. So I'm going to use this rep function to do that. So rep is replicate. So rep is going to, let's just copy that out of there. Rep15 is going to replicate this number or this thing here, whatever we give it, it's going to replicate it this many times. So it's going to replicate 1 5 times. So let's see what that does. Rep15 gives us 5 ones. And then we're going to do exactly the same, but we're going to replicate 2 for the right hand 5 times for 5 fingers. So there's rep25. And then this line here, this whole line is going to put those together. So it's going to rep 1 5 times, and then it's going to concatenate onto the end of that rep of 2 5 times. So there's hand. It's 1 1 1 1 1 for the left hand, and then 2 2 2 2 2. So now we've got our finger data lengths here, and matching against those is a vector that matches them perfectly, which tells us which hand they belong to. 1 for left and 2 for right. And now we can plot that. So we're going to plot that here using the plot function. We're going to introduce this new tilde notation. So we're going to plot fingers, the finger vector of finger lengths by, that's why you read that, that tilde is plot fingers by hand. So it's going to basically put hand on the x-axis and it's going to put fingers on the y-axis, because that's how we'd read that. So fingers, this is the thing we're interested in plotting, that always goes on the y-axis, and we're going to plot that against something on the x-axis. So there's a plot of fingers by hand, and we can go down here to the plot pane where it's appeared. So we've got 1 2 3 4 5 data points for the coded hand 1, so that's the left hand, and over here the coded hand number 2, it's got 1 2 3 4 5 finger lengths with it as well. So that's hand on the x-axis and finger length. So it's fingers by hand is how we read that. Now it's not the best picture in the world. There's a load of white space in the middle. That's pretty horrible. These are rammed up against the side. Also loads of stuff to be changed on this, like get rid of all these ticks, we don't need them. We maybe want to change that 1 to be a left and this 2 to be a right. We'll do that again in another podcast, but for now we'll just do this kind of quickly. We'll just change the x limits. So what I'm going to do is I'm just going to change the limits of this x-axis to sort of pull in this white space and give us a little bit more room on the other side. So I'm going to plot fingers by hand again. I'm just going to set the x-lim to be, so the x limits are going to be C again. So the first entry is the lower limit, the next entry is the upper limit. So the limits are 0 to 3. Instead of 1 to 2, it's 0 to 3. So that's what we end up with. So that's a much easier way to look at the data. So now at least we can see that the finger lengths here, we can see what the values of finger lengths are for the left hand, and we can see what they are for the right hand. And interestingly enough, it looks like my left fingers on my left hand are bigger than my right hand, which, yeah, go figure. I am right-handed actually, so I nearly would have expected it the other way if anything, but there you go. I'm asymmetrical in my hands. So that's a quick plot. That's an entirely sensible way to look at those data. Of course, if we had more data than that, I mean, typically we're not just plotting 5 data points against 5 data points, so we might have like 100 data points or 20 or 30 or something, a bit larger, and we'd there might be a lot of overlap between the data points here. Right now they spread out. None of my fingers are the same length, they spread out. But in a situation where they overlap more, there was loads and loads of data points, we'd need to aggregate or sort of summarize that data, because showing a whole scatter there would just lead to a cloud of blurred mess of overlaying data points. So one way to do that, and the quick way to do it, is to create these box plots. So a box plot is a way of summarizing data, and it's an example here. We sort of took through it recently. What it will do is it will take a scatter of data like this, and it will try to summarize it into some aggregate pieces of information to describe the distribution and spread of those data points. So over here, particularly this box is easier to see. This black line here is the median. That's a measure of the center. So the median means that 50%, so half the data points lie above that line, half the data points lie below that line. This box is then called the interquartile range. This box here is the upper third of the data. This is the lower first quartile. So a quartile is 25%. So this is the lower 25% of the data. This is the upper 25% of the data. So that means that together 25 and 25 is 50. So 50% of the data lie above and below this black solid median line. 50% of the data lie inside this box here. And then the extent of that box outwards is represented by these whiskers. So this whisker here will keep going up and up and up and up and up until either it hits the maximum data point. So if it hits the max data point, it will stop. Or if it gets to a point where it's 1.5 times the length of the size of this interquartile range here, it will stop. So it'll either go to the maximum, or if the maximum data point is too far away, it'll stop at 1.5 times the size of this box, and then it will draw the data points beyond that as data points. You'll be able to see that they're called outliers. They're beyond what you might expect them to be. That's basically it. We'll talk about box plots more in a subsequent podcast as well. Okay, so what we're going to do now is we're going to make a box plot instead of that data, the sort of scatter plot data that we've done up before like this. We're going to make a box plot. I'm actually going to change this code here. I'm going to change this to make it more similar to what we've done. Because one of the things I like doing with this use of the tilde here is to keep everything the same. So there's different ways of using the same function sometimes to end up with the same result, and this is one of them. So I'm actually going to change this. This would work just the same. This version of box plot will take 2 columns of data. So again, it'll take here the left and the right finger data. We go over here to the console. That's what it looks like there. So it will take 2 columns, and for each column it will draw a different box plot, and it'll label them according to the name. So that's kind of nice in a way that it works like that, but it's different to how we've just constructed it up above. So let's change that there to fingers by hand. I'm going to change it here as well. So let's run that. So fingers by hand. So we originally had our data points here like this as scatters. Now take a look at the box plot. Now if we look at the corresponding box plot for that, remember we've got 1 that's the left hand, 2 that's the right hand. Again, we could change those labeling, but I'm not going to do that here in this podcast because that takes quite a little bit more code to do. We'll do that again. But that then lets us see very clearly that the exact same data, those 5 data points, now summarized and aggregated as a box plot. Now again, with 5 data points in each box, I probably wouldn't do that. I would suggest if you've got 5 data points of that, I would just plot the raw data. But what you can imagine when you've got 10, 20, 30 data points, that this is a much sort of snappier, easier way to visualize what's going on in the data. So we can do something a little bit, we can embellish that a little bit here. So I'm going to show you a little bit of code here to do that again. So now we're going to change the label to the axis. So now we've got digit length in millimeters here, and we've got that's clearly not millimeters, is it? That's centimeters. So we'll change that. Digit length in centimeters, and then we've got hand written there. So we've got hand 1 and 2, which is left and right as per our coding. So another way we might do this, is with scatter plots. So another way to do it is because the fingers are matched. So obviously I've got the thumb on each hand, I've got an index finger on each hand. I can now then sort of pair them off against each other, and I can plot my thumb data for each finger I can plot it on this on an XY scatter plot. So to do that, I'm going to initially set up a plot. I'm going to set up a square plot because I want the axes to be perfectly square just for visual sake. So we do that with that par pty. Plot type is S for square. If you type $par, you will get a lot more options, help options for that. And now we're going to plot the right finger by the left hand. So we're going to get the right hand fingers against their corresponding left hand counterpart. And we're going to specify the X lab is the left hand, Y lab is the right hand. Specify X limbs between 5 and 10, Y limbs between 5 and 10, and that's aspect ratio is 1. So we're just customizing this plot a little bit. And the reason for that is I want to get a nice square plot. So that's the square plot with the PTY equals S option. So that's square. We've got the axes are equal, so the distance here between 5 and 6 is exactly the same as the distance here, so the aspect ratio is the same. Now we've got the left hand data here and the right hand data here on the y-axis, so this then will be one of my digits. I'm not sure which. I'm guessing thumb. Maybe it's thumb or little finger. I can't tell which. But so one of these then. So this is the same finger plotted against itself for the right and left hand. So that just lets us see they're not obviously they're correlated. My thumbs are sort of the similar length. My index fingers are the similar length. My finger 2, 3, 4, and 5 are all the similar length. And to help visualize that a little bit more, we can add a line of symmetry. So we can add the one-to-one line, this diagonal line up here, using the AB line function. So AB line is a function. It takes two values, and it takes two values to draw a line. You need the intercept and the slope. So A is the intercept, so that's 0, and the slope here is 1. It's the one-to-one line. So we can add that on with this. So that adds this black line, this black diagonal line onto the graph. So just by the way here, what you can see again, you can see that the left hand, because all the data points are below that line, the left hand values are slightly larger than the right hand values. If they were perfectly equal, they'd all be on that line. But because they're below that line, the left hand values are ever so slightly larger than the right hand values. And I'm half wondering if that's just because I pushed the ruler in harder with my right hand when I was measuring my left hand. So I measured it a little longer. I don't know though. Or else my fingers are actually longer on my left. Who knows? So that's another way of representing the data. If we go back to thinking about a distributional sense, we go back to looking at some histograms of the data. Again, we can make these histograms like this. So here's some code here. These let us explore. This is a histogram of the left-hand data. So again, because we've only got 5 data points, it's not hugely informative. But basically, we've got 2 fingers between 5.5 and 6 centimeters. We've got 2 fingers between 7 and 7.5, and we've got 1 finger between 8 and 8.5 on the left hand. And similarly, on the right, we've got again 2 fingers between 5.5 and 6. We've got 1 between 6.5 and 7, 1 between 7 and 7.5, and we've got 1 between 8 and 8.5. We can also use this par function before we create figures. We can use par to do something else. We can use par here to make the rows. MF row command is equal to C1 and 2. So that will make a multi-panel plot. Now when we do our 2 plots, we'll end up with 2 of them side by side on the one window. So it's a nice, quick, easy way to get the data for 2 groups up on the screen together and compare them visually. You can even change their color. The color option, the col equals, and the main, you can just change that title to whatever you want. So this is with 16 breaks. 16 breaks. We've got slightly smaller bin windows now that we're chopping the data up into. And again, much like before, you can calculate summary statistics. You can get the summaries of the left and the right data, the min, the median, the max, etc. And then if you want, so at the end of that, so there's a sort of a script file that loads in some data, creates a bunch of figures and plots that you might want to use to put into a project, a write-up or something. At the end of all that, you can, if you want, save your data out. Now, my advice generally would be, in nearly all circumstances, by saving your data, I mean save these objects. So these objects that exist down here in the environment, we're able to save those to file somewhere, and we save them into an R data file, which is .rda or .rdata.rdata for longhand, both the same thing. You can save those out and for later recall. Now, I would say for for the vast majority of cases, that's just not needed. You're far better off having a script that stores the instructions to do your analysis rather than the output of the analysis itself. And the reason for that is that it's much more reproducible, and it's easier to spot errors and problems or mistakes that you've made if every time you rerun your analysis again it's robust and it works and does what you think it does, rather than loading up some objects that you don't really have any record for how they were created. If I save these objects to file somewhere, there's no record for how those values were created, calculated, or manipulated at all anywhere. It's just gone. It's just a flat bunch of R objects that I could have faked for all anybody knows. So by having the instructions there, it's a much more robust, reproducible way of doing it. Now, that said, there are some occasions you might want to save these things to file. If your R script took ages to run, and it's entirely possible that a script could take an hour or 2 hours or even a few days to run, if that's the case, you don't want to be doing that every time. And in that situation, you might want to have both the script file and an RDA or RData file at the end of that, saving your objects out. The other time you might want to do it is if through the course of making your R script, some of the objects that are made are very, very large. They might contain thousands or even millions of data points in some simulated script, in a script that's simulating data or generating large quantities of data in the background. You might not want that hanging around in memory, just taking up space for no reason. So a kind of clean way of doing things that way would be to, if you create something massive like that you only need for a short period of time, or you don't need for the full analysis, you might take that object, save it to file somewhere, and then delete it from the current environment just to keep R lighter on memory, so it'll be faster and able to perform the rest of its calculations in your script. Those are the two obvious reasons why you might do it. But again, the vast majority of situations, I think, especially for people learning to do sort of relatively basic analyses in our small data sets, is you don't want to do this, but I'll show you how to do it anyway. So you can save your data out using a line like this. So for example, the function ls lists everything that's in the environment at the moment, and we can see in the environment pane what's there here, but up here in the console window we can access that information as well with the ls command. Now, you can then save each or any of these objects or all of these objects to a file if that's what you want to do. So I'll show us doing it here. So here we're going to save a file. So we're going to save all of them actually. So we're going to save fingers, hand, left and right to file. We could just save 2 of them. If I wanted to just save 2 of them, we might just write there C left right, and that then will just save the left and right objects to file. But let's save all of them for this situation. So that's list equals ls. So save expects something called list, and the thing it expects called list is a list of the objects to save. In this case, ls is going to generate that list for us. That's the list over here in the console window. And then it needs a file to which it will save them, and we're going to save it to a file called finger_data.rdata. Okay. Now, if I run that, that's going to save it to the working. This is where the working directory is important. That's going to save it to the working directory. So the get working directory at the moment is the project folder. So it's one up from the L2, the lecture 2 folder. If I want to save that into the lecture 2 folder, we would type L2 there, and then /fingerdata, and now that will save all of the objects in the environment at the moment to a file called fingerdata.rdata. So if I evaluate that line, we should then see, sure enough, a file has appeared here, this new symbol on it in the files pane called fingerdata.rdata. What that means now is, if I were to remove everything from the environment, so if I remove list equals ls, everything from the environment is now clean and gone. Now then, if I load the file fingerdata.rdata like that, it puts them back again. So that's them back. Okay, so we've used our script to run and create some objects. We've saved those objects to file, and then we've loaded them back up again. But like I was saying, I actually would discourage you from doing that at all. So then just at the end, if you fancy it, there's a little task for you to do, a little assignment here, and the suggestion is you measure your own left and right fingers, and you basically do much the same yourself, and you use the example script data that I've done here to recreate this analysis for your own data. And you might think you might want to measure something else that's sitting on your desk. You might want to measure heights of your family or friends. Instead, whatever you want, but I suggest you go try do this, collect some data yourself, and then don't make all these plots, don't just copy it all blindly. Pick and choose what plot you think's most appropriate to how you want to represent the data and what you think's the best way of describing to somebody what's interesting in the results that you found. Yeah, and explain your results. That's the important part. We don't just do this for fun. So try and explain the results and describe them to somebody in a markdown file, preferably. So that's it for this podcast. We'll pick this up again in topic lecture 3, which is going to be coming on to importing data. So instead of typing data in like we were here with the left and right and typing the data in manually, we're going to actually have data that's in an Excel file or a text file sitting on our computer somewhere. We'll use R to import that, and then we'll start being able to do much more normal analyses of data, summary statistics and graphs, etc.